I said earlier that in talking about a spin up, spin down configuration, that we have these spin operators Sx of h bar over 2, 0, 1, 1, 0. Sy is h bar over 2, 0 minus I, 0, and Z is h bar over 2, 1, 0, 0, minus 1. And this is a good choice because it fits with our commutation relation for Sx, Sy, and Sz. So basically those commutation relations give us this form. And what we do is we can actually clean it up a little bit, or basically create what's called the Pauli matrices, since Wolfgang Pauli is the one who worked a lot on spin, where basically the Pauli spin matrices sigma x is just the matrix. Sigma y is this matrix, and sigma z is this matrix. And therefore we can write in a kind of more compact form that S is h bar over 2 times the Pauli spin matrix. Now, once we've chosen our spin matrices to have this form, then what we can find is that there are different properties that you get. And so these properties of the sigmas are, one, they have an anti-commutation relation, where basically sigma I, sigma j, so that's the anti-commutator, which is saying sigma I, sigma j plus sigma j, sigma I. So he has a plus instead of the minus. Anyway, for the Pauli spin matrices, that's equal to 0. So you could work that out. Sorry, anti-commutation relation. So the anti-commutation of any two Pauli spin matrices is 0. And so you could work that out for yourself. Just take sigma x, sigma y, and put them into the equation, and then prove to yourself that that's true. So another property is, given we have this commutation relation for the spin matrices, so I said that was I h bar, the sum of the Levi-Civita tensor times the spin matrix, and we sum over all three, so basically 1 to 3, or if you sum over x, y, and z. Now if we put in the Pauli spin matrices, what do we get? Well, that's h bar over 2 sigma I, h bar over 2 sigma j, which is going to be equal to I h bar sigma k, I mean the sum of k goes 1 to 3, Levi-Civita, and then h bar over 2 sigma k. Okay, so if we work this out, I could factor out the h bar over 2's, so I get h bar squared over 4 is equal to I h bar squared over 2, this sum, and we can basically now divide out the, let's see, oh, okay. So we could write this down. Now let's work out the commutation relation. Well, let's get rid of the h bar. We can get rid of the h bar squared, and so what I'm left with is the commutation relation Clean that up. So we get the commutator of the polyspin matrices, which is equal to 2I, the sum. So we could just stop there, right? And we have a pretty useful equation for the polyspin matrices. We basically got rid of the Planck's constant part. But if we go a little bit further, if we write out the this commutation relation like this, if we remember from what we did in the first property, the anti-commutator, said that sigma I, sigma j plus sigma j, sigma I is equal to 0. So that means that sigma j, sigma I is equal to minus sigma I, sigma j. So if I put that into the commutation relation, I basically get sigma I, sigma j minus a minus sigma I, sigma j, which is equal to 2 sigma I, sigma j, which I now put back into the above equation. So I get 2 sigma I, sigma j is equal to 2I, the sum of all components, summing over sigma k. So now I can cancel out the 2, and I have this relationship that the product of any two, not just the commutation relation, but the product of any two polyspin matrices is equal to I times the sum of components x, y, and z, add in the Levi-Civita, and I get sigma k. So now it's not even just the commutation relation I can take advantage of, but it's just the product of two polyspin matrices that I now have a formula for. I can calculate that easy without having to do a lot of matrix algebra. Okay, so a third property of the polyspin matrices is that they are traceless, which basically means if I take the trace of any one of them, it's going to be equal to 0. And so if you remember, the trace of any matrix is just going to be the sum of the diagonal components. So in this case, it would be 1, 1 plus 2, 2, let's say. So if we look at it, the trace of sigma x is the trace of 0, 1, 1, 0, which is just 0 plus 0 is 0. The trace of sigma y is 0 minus I, 0. Again, it's 0 plus 0 is equal to 0. So now let's look at sigma z. So the trace of sigma z is 1, 0, 0, minus 1. It's a good choice for this matrix. 1 minus 1 is 0. So for all three polyspin matrices, they're traceless, which could come in handy if we're ever trying to diagonalize our matrices. Okay, so property 4. Property 4 says that the square of any polyspin matrix is the identity. So the square of any polyspin matrix is equal to the identity. So that'll come in handy. Or we could write this down as, if you just look at the dot product of all three components. Whoops. Squared is equal to the identity. So Anyway, so how could we do this? Well, we could use property 2, which said, the product of sigma, the sigma I times sigma j is equal to basically the sum overall. Or we could take a look at just from quantum mechanics, the square of the spin projection, say in Z, of a state, S with a projection M sub S. So it should be equal to so that's SC H bar over 2, and then I get the state back again, which is equal to H bar over 2 times H bar over 2, and I get the state back again. So basically the eigenvalue is H bar squared over 4. Now, if I move this to the other side, I have SZ squared operate on the state minus H bar squared over 4 operating on the state. That should be equal to 0. So SZ squared minus H bar squared over 4, the identity matrix, is now operating on the state. Basically, I factor out the state, which means that these operators have to be equal to 0. So I could write this out now. I can factor it. Like so. Now, if I generalize it to all directions, so now if I put this all together, it basically means that n, this quantity squared, is equal to H bar squared over 4 times the identity. And since the spin operator is just H bar divided by 2 times the Pauli spin matrix, then I get n dot H bar over 2 sigma squared is equal to H bar squared over 4 times the identity. And if I now factor out the H bar over 2 and square it, I get H bar squared over 4 n hat dot the Pauli spin matrix squared is equal to H bar squared over 4 times I. Divide both sides by H bar squared over 4, and you get n hat dot Pauli spin matrix squared is equal to I. Which basically means, now if I break it down into every single component, I would just get sigma squared x sigma y squared plus sigma z squared is equal to I, which basically means each of those components has to be equal to the identity. Okay, so I'm going to stop there. But there are still more properties of the Pauli spin matrices, and I'll talk about that in the next video.